Hello, everyone, and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. I also got my Bachelor's of Science at this institution as well in pharmaceutical chemistry. Today, we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with tutoring or with homework even, then check out the links in the description below. So now we're going to get started on the set of questions for today's session. All right, so the first question asks, how many ounces are there in a liter? Okay, so to answer questions like this, we simply just need to know how many ounces there are in a liter. So there are actually 33.8 ounces in 1 liter. Yeah, that's all that there is to it. So let's see what our junior tutor said. You have to know the conversion factor. The US and the imperial system of units have different values. So in Canada, we just go by the US value where 1 liter is equal to 33.8 ounces. For the imperial values, 1 liter is equal to 35.195 ounces. So it depends on which country you are residing, which conversion factor would be appropriate. Okay, so this solution is correct. Okay, so let's move on to question number 2. What is a heterogeneous mixture? So when you have a heterogeneous mixture, this is when you have 2 or more substances mixed together and you can see them as 2 distinct phases. So for example, let's say we had some kind of liquid, and in this liquid, I'm gonna add in this red square substance. This is an example of a heterogeneous mixture. I can visually see 2 distinct phases. So the opposite of a heterogeneous mixture would be a homogeneous mixture. This is when you have 2 or more substances mixed together. And as you can expect, since it's the opposite of heterogeneous, the composition is uniform. So let me draw out that same liquid, but this time I'm going to show that I'm going to add like blue cubes in it. When you have a homogeneous mixture, you can't differentiate the two, and like those cubes will fully dissolve and you just get a single phase. So there's no distinct like two phases. When you mix them, they just mix in well. So let's see the answer from our junior tutor. Heterogeneous mixture is a mixture of two or more substances that appear as two distinct phases. An example of this would be pebbles and sand, or oil and water. Two examples result in a mixture with two clear components. So this solution is correct. Okay, so now let's move on to question number 3. What is dehydration synthesis? So let's first just analyze the word dehydration. On the right side, you have hydration, so something involving water, and then there's a prefix of D in front of it. So it's kind of like the removal of water. But I'm also just going to write down the actual definition of dehydration. It's a reaction where you have two molecules that condense together and water is formed as a byproduct. So even though, like, even if I saw like a multiple choice and I need to define what dehydration is, like even just looking at the word, it has something to do with water and it has a D in front of it. So it's kind of like water was removed. So I'm going to draw out an example of like one of the more common dehydration reactions involving two amino acids. So for this example, I'll draw out one of the amino acids. I'm going to put just an R to show that it can be any side group. And then I'm going to draw just a second amino acid beside it with a different R group. And now I'm going to circle where these two reactants will combine. And then I can draw a final product at the bottom here. And color code it. Okay, so you can see where the two amino acids come together. And I'll also write that water was formed as the byproduct. And this is an example of a dehydration synthesis. So let's see the answer from our junior tutor. When two smaller molecules are combined through the removal of a hydrogen atom and a hydroxide anion from the two molecules, generally between the same or different monomer units, it results in the formation of a larger molecule and a molecule of water due to the elimination of a water molecule, which is also known as a condensation reaction. Along with the formation of a new molecule, it is called a dehydration synthesis reaction. So the dehydration synthesis occurs in many biochemical reactions, such as the formation of carbohydrates, triglycerides, proteins, and nucleotides. An example of dehydration synthesis is the formation of covalent bonds between a carbohydrate and any other molecule called glycosidic bonds. For example, when two glucose molecules form one maltose molecule with the release of one molecule of water, a glycosidic bond is formed. This is well explained, and the solution is correct. Okay, so now let's move on to question number 4. If a solution is 0.5% weight per volume, how many milligrams per milliliter is that? Okay, so let me just write out that this is question number 4. So first, I'm just going to talk about percent composition. Just so that we have like a background on it. But basically, this is when you have the weight per volume. And typically, it is in grams per milliliters times 100%. So let's look at the question. If we have a 0.5% weight per volume solution, that is the same as saying we have 0.5 grams per 100 milliliters of solution. So I'm just going to convert this from grams to milligrams. And to do that, I'm going to use the conversion factor of 1,000 milligrams per 1 gram. Then if I multiply it out, I'll notice that my grams cancel out. And then I'm left with 5 milligrams per milliliter. So let's see what our junior tutor said. Recall the formula for percent composition. This is shown in equation 1. So this is the same formula I have, where percent of weight over volume is equal to grams per mil times 100%. Since we have 0.5%, this means that we have 0.5 grams of a solute per 100 milliliters of solution. To solve the problem, we need to perform some dimensional analysis. The calculation is shown below. And you can see they also got 5 milligrams per mil, and this solution is correct. Okay, so let's move on to question number 5. How would you calculate the molar mass of water? Okay, so for the molar mass of water, first we need to find out our atomic masses of hydrogen and oxygen. So these are values that you would just find on the periodic table. For the molar mass of hydrogen, it's 1.01 grams per mole. And the molar mass of oxygen It's around 15.99 grams per mole. So now I want to find the molar mass of water. It's simply going to be 2 times 1.01 grams per mole. So this is because there are 2 atoms of hydrogen for every 1 water molecule. And then I'm just going to add just 1. I'm going to show that there's only 1 atom of oxygen times 15.99 grams per mole. So we end up getting 2.2 plus 15.99. And then we get a final value of 18.01 grams per mole. Let's see what our junior tutor said. In definition, the molar mass is the mass of a given chemical element or chemical compound in grams, divided by the the amount of substance in moles. The molar mass of a compound can be computed using a periodic table by adding the standard atomic masses in grams per mole of the individual atoms or elements. It is used to compute for the number of moles of a certain compound to give its mass. To compute for the molar mass of water, we need to get first the individual atomic masses of each element. Remember that for every 1 mole of H2O, there are 2 moles of hydrogen and 1 mole of oxygen. Therefore, we need to multiply the atomic masses of H and O to 2 and 1 respectively. So here they just have the 2 atomic masses of hydrogen and oxygen. And then solving for the molar mass of water, we have H2, which is 2 times 1 is equal to 2. Atomic mass of oxygen, 16. So they got that the total molar mass of water is 18 grams per mole. It's the same thing as what I got, except just rounded, but it's still correct. So this solution is correct. Okay, so now let's move on to question number 6. How many quarts is 4 pints? So first we need to know the conversion factor. 1 quart is equal to 2 pints. So now that we know this, we are looking for X quarts in 4 pints. And then on the right side of this formula, I'm just going to put that there is 1 quart is equal to 2 pints. And then you just simply solve for X. So if you have trouble with conversion factors, you'll notice that your units should cancel out nicely. So pretty much this is just 4 divided by 2. Our pints should cancel out and we should be left with quarts. And you get X is equal to 2 quarts. So let's see the answer from our junior tutor. To convert pints to quarts, we need to remember the conversion factor. 1 quart is to 2 pints. Using this conversion factor, we can solve this as quart is equal to 4 times 1 over 2, which is equal to 2. This solution is correct. Okay, so now let's move on to question number 7. What is the Lewis structure of NH3? Okay, so this is a multi-step question. So I'll just go over it one by one. The first step is to find the total number of valence electrons. Okay, so let's see what we have for nitrogen. For one atom of nitrogen, there are 5 valence electrons. And then for hydrogen, each hydrogen has 1 valence electron. And since there are 3 of them in NH3, I'm going to multiply this by 3. So we end up getting a total number of 8 valence electrons. Okay, so step 2 is just to connect atoms. So just since we're given NH3, on the right here, I'm just going to draw my nitrogen. And then I'm going to draw out my 3 hydrogens. And you'll also notice that there is a single bond between all of them. And each bond involves 2 electrons. So I'm going to take note of that, where each bond involves the sharing of 2 electrons. So let's look at how many electrons we have drawn so far. So if we count out that there are 3 bonds, that means there are 6 electrons involved. But since we counted out a total of 8 valence electrons, this brings us to step 3, which is to assign electrons to your terminal atoms. So in our case, this is hydrogen, but hydrogen can only have 1 electron involved. So you'll never see hydrogen have like a lone pair or anything. I'm just going to put in brackets none for hydrogen. But for step 4 is to assign electrons to the central atom. So we need 2 more electrons for NH3. So I'm going to put them on my central atom, which is the nitrogen. So all of our electrons should be accounted for, but I'm still going to write down the last step, which is when if you have no unassigned electrons, but your central atom doesn't have an octet, this is when you can make double or triple bonds. So in our case, let's look at the nitrogen. It has 2 electrons as a lone pair, and then it has 3 bonds attached to it, each bond involving 2 electrons. So that means it has its octet. So this is our final Lewis structure for NH3. So let's see what our junior tutor said. The Lewis structure of ammonia, NH3, is 3 hydrogen atoms bonded to a nitrogen atom, which is in the center, with a lone pair of electrons on top of the nitrogen atom. The Lewis dot structure represents the arrangement of electrons, shown as dots, between atoms in a molecule. The atoms must follow the octet rule or the tendency of atoms to prefer to have 8 electrons in the valence shell. The individual formal charge of each atom, as well as the overall formal charge of the molecule, must be satisfied. So, in drawing the electron dot structure of ammonia, step 1, draw the skeletal structure of NH3 with nitrogen at the center. Step 2, calculate the total number of valence electrons in the molecule. So this is what we did first, where you had the number of valence electrons in nitrogen plus in hydrogen. They got 5 plus 3 equals 8. Step 3, distribute the electrons as dots. Note the octet rule must be satisfied for nitrogen. However, hydrogen can only share 2 electrons. Step 4, replace the 2 electrons with a single bond between nitrogen and hydrogen. A lone pair of electrons will be left at the top of the central nitrogen atom. Okay, so we had similar rules, but just in like different orders. So it just depends on what method you feel comfortable with doing. But overall, this solution is correct. Okay, so question number 8 is another Lewis structure question. What is the acceptable Lewis structure of ozone, which is O3? So again, we are going to start off by finding the total valence electrons. So for oxygen, there are 6 valence electrons. And since there are 3 oxygens in O3, we're going to multiply it by 3, and we end up with a total of 18 valence electrons. Okay, so now I'm just going to draw all my oxygens out like this. So with each bond, there are 2 electrons involved. So right now I have 4. And the next thing I want to do is just write out all the valence electrons on oxygen, the terminal oxygens. Okay, so let's count out how many this is. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So you can see that this is already too many electrons than we need. So I'm going to erase one lone pair of electrons from one of the terminal oxygens. Make a double bond. And we want our molecule to be neutral overall. So if we have a positively charged oxygen, then one of them has to be negatively charged in order for it to be a neutral molecule. Okay, so let's see what our junior tutor said. A Lewis structure is the representation of the arrangement of valence electrons among the atoms in the molecule. Some guidelines in writing Lewis structures are to sum the valence electrons from all the atoms, use a pair of electrons to form a bond between each pair of bound atoms, then arrange the remaining electrons to satisfy the octet rule. So note that the correct Lewis structure would be the structure that would have the simplest formal charge. Let's apply the guidelines to ozone. The sum of the valence electrons for ozone is 18, since one atom contributes 6 electrons. Now we form the bond. So they used 4 electrons to make the 2 bonds, which leaves us with 14 electrons. The middle oxygen needs 4 electrons to complete an octet, while the other 2 oxygens on the sides need 6 electrons each. This means we would need a total of 16 electrons, which we do not have. So we form another bond. We use 6 electrons to make one single bond, and one double bond, leaving us with 12 electrons left to arrange around the oxygen atoms. The middle oxygen needs 2 electrons to form an octet. The oxygen on the right needs 4 electrons, and the oxygen on the left needs 6 electrons to form an octet. I think they mean on the right for this part. We would need a total of 12 electrons, which we have. Giving the electrons to the oxygen atoms, we get this structure. Now we assign a formal charge using this equation. So they have formal charge is equal to the number of valence electrons minus the number of electrons in a lone pair plus the number of electrons participating in the bond divided by 2. Formal charges from left to right are 0, +1, and -1. Check if this Lewis structure is correct, I guess. We give another 2 electrons to make the single bond into a double bond. The structure would be this. In this structure, the middle oxygen is already a complete octet. The 2 oxygen atoms on the side need 4 electrons each. Now that we used 8 electrons to form the 2 double bonds, meaning we still have 10 electrons left, this means that we would have an excess of 2 electrons, which we cannot assign to any other oxygen atom since all of them would have complete octets. Therefore, this structure is incorrect, and the correct structure would be the previous one shown below, along with the formal charges. Okay, so this is the structure I have as well. So this solution is correct. Okay, so let's move on to question number 9. What is the Balmer-Rydberg equation? Okay, so I'm just going to write it out down here. I'm going to write RH to show that this is the Rydberg constant. Then I'll explain what these variables mean as well. Okay, so this is the Balmer-Rydberg equation. So lambda stands for wavelength. And the units are in meters. Okay, so like I mentioned earlier, this R is the Rydberg constant. And it is 1.097 times 10 to the 7 inverse meters. So this NF is the principal quantum number of the initial state of your electron. Oh, I mean final state, sorry, this is NF. And then as you can guess, Ni is the principal quantum number of the initial state of your electron. So sometimes you'll have a question where they ask, like, what is the wavelength when an electron goes from a quantum state of n equals 4 to n equals 1? Then you would just plug it into this equation and then solve for wavelength. Let's see what our junior tutor said. The Rydberg formula calculates the wavelengths of a spectral line in many chemical elements. These wavelengths are formed when an excited electron from a higher energy state returns to its ground state and releases energy. Specific wavelengths or frequencies or energies could be predicted based upon a constant and two integers. The interpretation was that one integer represented the initial state and one integer the final state. The wavelength or frequency or energy was related to the change that occurred moving between these two states. Yeah? And then they have the Rydberg equation is represented as this, where lambda is the wavelength of electromagnetic radiation emitted in a vacuum. R is the Rydberg constant for hydrogen. And I is the principal quantum number of the initial state of the electron, and then NF is the principal quantum number of the final state of the electron. So this solution is correct. Okay, so now let's check out question number 10. How do you convert grams to kilograms? So basically, 1,000 grams is equal to 1 kilogram. So if we know this conversion factor, we can answer the question. So let me write out an example for this. What is, like, I'm just gonna make up a number. What is 25,600 grams in kilograms? Basically, I always like to write what I'm looking for at the top. So x kilograms over 25,600 grams. And then I put my conversion factor on the right. 1,000 gram, 1 kilogram. Okay, so whatever your desired units are will always be the numerator, and then whatever you're trying to get rid of and whatever you start with will be in the denominator. So you know you did it right if your units cancel out nicely. So this is the same as saying it's 25,600 divided by 1,000. And then you end up with x being equal to 25.6 kilograms. Let me write out like a second example. What is like 15 million 25 grams in kilograms? Again, it's going to be x over whatever value is given. Moving that over to the right side. So basically, you can also picture your decimal moving 3 spaces to the left. So like 1, 2, 3. And then you end up with 15,000.025 kilograms. So we can also write this in scientific notation. Let's say 1.5 times 10 to the power of 1, 2, counting the decimal. 1, 2, 3, 4 times 10 to the power of 4 kilograms. Okay, so let's see what our junior tutor said. In converting grams to kilograms, we simply remember that 1,000 grams is equal to 1 kilogram. To convert grams to kilograms, just divide the given amount in grams by 1,000. Yep, pretty much. This solution is correct. Okay, so I think we have time for one more question. What is the molar mass of carbon dioxide? Okay, so carbon dioxide is the same thing as CO2. So basically, we need to first know the atomic mass of carbon and the atomic mass of oxygen. Okay, so these are the values you would just find on your periodic table. For carbon, it is 12.01 grams per mole. And for oxygen, it is around 15.99 grams per mole. And then to find the molar mass of carbon dioxide, all it is the molar mass of carbon plus 2 times the molar mass of oxygen. So this is because there are 2 atoms for every 1 molecule of carbon dioxide. So let's plug these values in. You get 12.01 grams per mole plus 2 times 15.99 grams per mole. So just simplifying it, 2 times like 16 is around 32. 12.01 plus 32 is around 44.01 grams per mole. Let's see what our junior tutor said. The molecular formula of carbon dioxide is CO2. To compute its molar mass, we need information about the molar mass of carbon and oxygen. This can be seen in the periodic table of elements. Carbon has a mass of 12.01 grams per mole, while oxygen has a 16.00 gram per mole mass. To find the molar mass of CO2, we just add up the total atoms present in the compound, 1 carbon, 2 oxygens. That is MCO2 plus is equal to MC plus 2MO is equal to 44.01 grams per mole. So this solution is correct. Okay, so that is all the time we have for today. And if you like today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description below. And also don't forget to leave a thumbs up and a comment if you like today's video, and also share it with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.